Now, all of this also leads us to some interesting insights, which basically tells us that the verification strategy for hierarchical design should be to verify each module independently. Ideally, I have a test bench that just checks whether my adder tree is working properly. I have another test bench that checks whether my partial product generation is working properly. Maybe these are simple enough that I don't really need to have separate test benches for them, but the idea remains the same, right? Even if I go for slightly more complex designs, I should try to break them into individual units that can be tested and verified to work correctly on their own. This also basically leads us to this idea of unit tests, right? Unit tests are essentially focused test benches for each module. So for example, I could have a partial product generator test bench, another adder tree test bench, right? It is possible to go too far. You might, for example, have a half adder test bench. You don't really want that to come into play when you are trying to design, let's say, a 16-bit or a parameterized adder, right? Instead, or a parameterized multiplier, right? You want to be able to work at the level that sort of makes sense for the design that you are currently doing. Now, you also want to have integration tests, and what that means is how we are doing this kind of hierarchical design is to integrate multiple different modules together, partial product and adder in our case, into a larger block, which is our multiplier. So naturally, that also leads to a hierarchy in terms of the test benches. And finally, what we have is there is this notion of so-called coverage driven verification, right, which basically says that we have a certain amount of code that we have written, and we want to answer the question, how much of this design is covered by tests? What do we mean by covered by tests? It basically says, is there some part of a test case that at least exercises this particular line of code, that causes this particular line of code to respond in some way? And ideally, we should be able to say, okay, can I sort of test all the different variations of what this particular line of code does, right? Now, this part of it is strongly related to aspects of software engineering, right, and which basically come in from the notion of how we build software systems as well. It is very useful in the context of hardware design, because a lot of hardware design that we are doing can be thought of at some level as software development, right? It works in very much the same way. So the approaches that we follow, how we go about designing, documenting, testing, and finally maintaining, in the sense that how a change is sort of recorded and maintained in a certain way, a lot of those owe their practices to ideas from software engineering, including things like version control and so on. Coverage driven verification is also one such, right, and it's a very valuable approach to follow. But right now we are not going to be talking much about test coverage, right? We are going to be talking primarily about the design process itself. Now, in the context of FPGAs, what is the role of this whole hierarchical design? Well, it plays a number of useful roles, right? It can typically improve the placement and routing performance because the tools are able to work on individual modules and try to optimize them. It also results in faster compilation times, right, giving you better performance in terms of how quickly we are able to compile a large design, because each individual design can be compiled and optimized on its own. In particular, you might also be able to take advantage of something called incremental compilation, where if you make a change in one module, let's say that you have a bug in your adder tree and you fix it, you don't need to go back and recompile the partial product generator. That's already done, and you can take advantage of that without recompiling the entire design in order to get speed ups and probably even better performance overall. It also means that we can make use of integration of pre-verified IP, intellectual property cores, right? These are typically designed and either sold or given for free. So the Xilinx tools, for example, come with a large set of pre-verified IP cores that we can use. There are also a number of cores that are sold commercially, right? So it is possible for individuals or companies to focus primarily on designing IP cores that are then sold to others rather than just designing full systems on their own. It also helps with this aspect called timing closure, which is something that we will be talking more about as we get into details of how exactly systems are implemented and analyzed in terms of timing.